Good morning, all. So, this is one of the lectures which was given on the conference on BIT Misra on 15 and 12th December 2024. And the topic of the lecture, as you can see, is based upon the data storage or next generation data storage. Now, we all know that we use hard disk drives, right? We use which has been now replaced by this solid state drives. Okay, so these we previously used to use this hard disk drives, which was based upon the magnetic storage. We had some read and write heads, and there was some rotating disk, and information was imprinted on it, and it was based upon this giant magnetoresistance, and spintronics was is also coming up and has been incorporated in these devices. Now it has been replaced by this solid state drives, uh, which are faster. Now the reason for these solid state drives to be faster is because they use non-volatile memory systems. By non-volatile, it means that even if you plug off the source, the data is still retained. And secondly, they use another technology called peripheral component interconnect, which was developed by Intel in 1990. Now, this peripheral component, what it does is it actually connects the interferal accessories, and sometimes it can even bypass the CPU. So that actually gives it a higher data processing rate. All the modern operating systems and PCs and tablets and all, they use this SSD drives to store data. Now, although these SSD drives are faster, and the hard disk, in terms when you talk about the bulk storage of data, like the cloud storage or the Google or the YouTube or the media libraries, it is still dependent on these hard disk drives. Now, if you take notice on the metrics, uh, the storage capacity of a solid state drive at present per device is around 10 TB, with a higher transfer speed. This is 15 GB per second. This is mainly due to this PCLE technology. However, in terms of storage, the hard disk drives are much ahead. Still, it's a 30 TB right now in 2024, and it will increase. It is supposed to increase to 50 TB per device till the end of this decade. Now, there are some more emerging technologies which are coming up in the near future, like a flash storage system, which is based upon NAND, that is Universal NAND Gate, and persistent memory system. Now, these two technologies are even being used in these solid state drives. Apart from that, a holographic or optical disk technique is coming up, which is basically capturing the holographic image and storing the information there. And most importantly, this DNA storage system is coming up, where they're using the nitrogenous bases, that is adenine, guanine, cytosine, and thymine, and they are linking these nitrogenous bases to binary numbers. Okay. By doing this, DNA can store 1 EV per gram. Okay, now what is this 1 EV? 1 EV stands for the exabyte. Sorry. 1 EB stands for exabyte, which is 10 to the power 18 bytes, right? Which is 10 to the power 18 bytes. If you go in the decimal system, whereas if you go in the binary system, it is called exabyte, and it stands for 2 to the power 60 bytes. Now, this is also equal to 1 billion gigabytes. So this amount of energy, this amount of information can be stored in a DNA. Now, 1 zettabyte is 1000 exabyte, and this amount of data is being stored by the cloud storage systems. When we say cloud storage, it appears that we don't require any physical space to store them, but it is actually not correct. For whatever the cloud storage systems that we know of, like Google and YouTube, they have this huge data centers, mainly in these countries, but also some other countries. Like for YouTube, this is one of the examples of the data storage system of YouTube, which is in Northern Ireland, where you can see how much space has been taken to store the YouTube data. And this is one in Frankfurt. This is for the Google. Now, this YouTube basically relies on the Google global network of data centers. Now, to just give an example, the amount of data there in YouTube, 500 hours per minute of videos are being uploaded, and the data again is subdivided into two categories. One is the hot storage, mainly which deals with videos that are very frequently accessed, and the ones are the cold storage, which are mainly which videos are archived. So, so this amount of data, and it is still growing. The amount which is required in the future is still growing, and so, and this is mainly due to the high resolution videos, that is 4K and 8K, which require higher data, higher space to get stored. So, and these all are hard disk drives. So the moral of the story is we still require, or the technology to increase the hardness, increase the data storing capacity of hard disk drives is still on the rise. Okay, so okay, so this brings to the next question is that how we can actually increase it. What are the areas which can be improved to cause an increase in the data storing capability of hard disk drives? Now, as we know that giant memory instance is or spintronic is being used for storing data in hard disk drives. So the main aspect is the size limit and the speed limit of transfer. Now, the limitation, or I shouldn't say limitation, or the areas which are improved for higher data storage is the which can be improved is the direction of magnetization. That is, it is random. We need to have a control in it. If you would like to increase the size limit, and the magnetization is not deterministic, like how many picosecond per bit, which is also has to be taken into control. Now, to do all these aspects, what we require is what we have designed is the following. Right. What we have designed, we have we have designed a ferromagnetic antiferromagnetic layer for the mandatory resistance part. And to go a step forward, what we have done, we have tried to pattern this ferromagnetic and antiferromagnetic layer. That, like, previously used to have layered. So this is ferromagnetic and this is antiferromagnetic. Now we would like to pattern it like different unit cells, right? Different, like in a crystal. So to do that, what uh, the process that we have adopted is using ion beams. By the process of ion beams, we have there is a phenomenon called dewating. Like if you put mercury, liquid mercury, on a flat surface, due to high surface energy, it forms globules like this. A similar phenomena takes place when we hit some of the metals with ions, and the top surface, they acquire higher surface energy and form globules like that. So it actually gets into different patterns. So this technology, this phenomena has been utilized to pattern the surface and to make it look like different units. So it actually resembles a metamaterial, where it is artificially engineered material with different units which have a collective phenomena or a coupling between them. So this is how the device looks like. So you can see a silicon substrate was taken, which was initially coated with, or it has an initial coating of silicon dioxide by oxidation, and by template patterning, focused ion beam and etching, followed by RF monotron, then from deposition, the following structure was fabricated. So we have this ferromagnetic antiferromagnetic layer, which is causes this exchange bias, but they are now separated by this insulating layer. Now, the material which was taken for forming this ferromagnetic antiferromagnetic system was cobalt on cobalt oxide. Now, the reason this material was chosen was because cobalt has a tendency to get patterned into the structure we are requiring. Like cobalt, if you, with the help of heat, can get patterned into these different the dewating of the cobalt can take place, like the one which has been shown here. That is why cobalt was taken, and the antiferromagnetic system was again cobalt oxide. Now, this exchange bias, what is this exchange bias? This is shift of this hysteresis slope. So this shift basically takes place due to pinning of the ferromagnetic magnetic moments. So if you have a ferromagnetic antiferromagnetic system at the interface, the ferromagnetic moments gets pinned by the influence of this antiferromagnetic moments. So you have a region where the moments are pinned. So this actually gives rise to the shift of this hysteresis loop to one of the sides. This is actually the exchange bias. Now, this is what happens in the case of a layered system. Now, since we have, apart from this exchange bias delivering material, we also have an insulating material which actually separating this exchange bias systems. Now, due to this presence of this insulator, uh, the it actually forms a magnetic tunnel junction, which is basically transfer of spin current or spin paralleling polarized current. Okay, so this, what is the spin polarized current? This is due to the formation of spin. So this is spintronics basically coming into the picture, where you have something called TMR, trimagnetary resistance. So you have parallel and anti-parallel spins which can get transferred through tunnel mechanism from one of the system to another system. So from this system, it can go to this system. So basically you have a ferromagnetic layer on the top, and from the ferromagnetic layer to go to the next adjacent ferromagnetic layer, the spins tunnel through this insulating barrier. So this is what forms a magnetic tunnel junction. And so what do we have here is an exchange bias and magnetic tunnel junction. Now the advantage that we have in this system is that the exchange bias, it actually stabilizes this magnetic tunnel junction. How does it what is the way by which it stabilizes? Now because the magnetic moments are pent, so it has a reduced thermal effect, first of all, and due to this there is a non-volatile memory system being established, that is data retaining without power, like we have in the case of non-volatile systems. So this what gives this system an added stability, and compared to if it had been only a ferromagnetic exchange from spin exchange between two ferromagnetic layers. Okay, now this exchange bias is giving it an added stability, and this system again can be used in making other devices like spin torque oscillators and RF detectors. Now, so this was the experimental results. As you can see, a cobalt on cobalt oxide system was formed by Mantron sputtering. It was done at the whole experimental was done jointly at Nuclear Science Center, New Delhi, IOP Bhubaneswar, and ICS Calcutta. Now, what we have here is a system having cobalt on cobalt oxide first deposited 24 nanometers each, and this was subjected to a low energy ion beam, that is 200 kilovolt argon at a fluence of 10 to the power 15 ions per centimeter. This was irradiated on the system, and you can see the formation of the different globules. So this is what represents the different unit cells of or different units having separate exchange pairs. Now the image plots of this system were taken at, and the temperature was also varied. The blocking temperature was around 300 Kelvin, and the exchange bias can be observed. And another thing that is observed is that increased in coercivity, that is this width, it also increases. Now the exchange bias again was found that it it varied from less than 1 to higher than 1 with temperature decrease. That is, it changes from positive to negative. Now this with increase in temperature, with decrease in temperature. So what we can infer is that with higher temperatures, we have taken the mode value. If we hadn't taken the mode value, we have only seen the absolute value. With higher temperatures, there is a reversal of spin occurring in the pinned region. So in this region, this is the pinned region, there is a reversal of spin occurring, and there is also a weakening of this ferromagnetic and antiferromagnetic coupling, and leading to imbalance and all. So this was one of the observations found. So it seems that this system works a little bit on lower temperature side. As we go up in the temperature, so the ferromagnetic and antiferromagnetic coupling is not that efficient as found in the lower temperature, and the similar observations were found by other groups as well. Okay. Another aspect which can be used in this system is the exchange bias induced MEMS cantilever. So, a MEMS cantilever was developed at IISc Bangalore under the INUP program, where we have used standard lithographic techniques to create a cantilever system. So, this cantilever system is basically a silicon nitride probe on a silicon substrate. If somehow we could modify that device or modify the system by having, not instead of having a silicon nitride substrate, we can have again this ferromagnetic antiferromagnetic layer on the substrate, on the probing region. That means it will look like this. So again we will have an exchange bias units at the top. So this again will lead to a formation of an exchange bias induced MEMS cantilever. Now, as it has done in the case of magnetic tunnel junction, again the thermal stability and the mechanical stability will be there, and the exchange, and it will act as a device, a sensing device. For in the case of, it will detect the magnetic fields, so it can detect, it will be able to detect weak magnetic fields. It can be used in magnetic cardiography, and it also can be used in the case of position and velocity sensors and microactuators. Now we do have a problem with this sort of cantilever systems. The problem is sensitivity issues. If you look at a cantilever structure, one side is clamped. So the one which is closer to the clamping region is less sensitive rather than the one which is away from the cantilever region, simply because it undergoes higher vibrations. So clamping effect increases as you go towards the clamped region. So this may cause some sensitivity issues. The problem, to solve this problem, we can use this pedestal design, where instead of having one clamp, you can have 4 clamps. And this has been found to be effective in having higher sensitivity. So it can act as arrays. It's not that only single cantilever system is there, so it can act as arrays. And if we could somehow deposit this exchange bias system on the top of these 4-sided pedestal cantilever, then what we are aiming for can be achieved. Now there is a spring mass damper model associated with this system, cantilever system, which also gets modified if we are adding some extra layers on the top of the already existing layers. This again will come into the picture. So the device will be more homogeneous, and it will, therefore it will lead to more enhanced sensitivity. Okay, so what are the takeaways from this discussion? The takeaways is that we can have a patterned cobalt on cobalt oxide systems, and the patterning can be done by ion beams, by the process of debating, and this will ultimately lead to a coupled exchange bias coupled monoclonal junctions for improved data storage as well as transmissions. And what we have observed is that there is a variation of exchange bias with temperature, and it is due to the interfacial spin reconfiguration and the competing anisotropies. And then we move on to this MEMS cantilever systems. We can design a design of a novel MEMS cantilever system has been proposed, and if we add the pedestal cantilever to it, the improved sensitivity, the cost and improved sensitivity of the device. Okay, so that's that's it.